Yeah, thank you, Ben, and thanks everyone for coming, and thanks for having me here today. I'm going to tell you about some recent work on sum of squares lower bounds for sparse random graph. And this is based on joint work with Chris, Aaron, and Gautam from U Chicago and Mother at TTIC. And I hope in the end of this talk, this diagram we're going to make sense of it. But yeah, let's get started. The problem we consider today is we sample a random graph G from G and D over N, which is an Erdos Jenny distribution, in which we sample each edge with probability D over N. So for this talk, think of D as being polylogarithmic, log square or some polylog. And the question we want to ask is, if there is an independent set of size omega for a given omega in the random graph sample G. And we know the true answer is going to be N log D over D. For there's a constant 2, but let's ignore constant for the talk. And the upper bound is easy by first mode method, and then we also know lower bound by Adam Fitts result. And for this problem, the algorithmic result we know before is special algorithm works when omega is at least N over root D. And what do I mean by a special algorithm that works? I think of it as a refutation algorithm that it outputs a number A of G for a given graph G such that A of G is always an upper bound, like it's always bigger than the mass independent set in the graph. And ideally, we want A of G as small as possible. However, as you can already see here, like there's a huge gap here between N over root D and N log D over D, like this square root D gap. And how does special algorithm work? You can think of it as we are given a graph G and consider the matrix Mg, that is the adjacency matrix, subtracted by the D over Nj, which is the normalized all-one matrix. So this matrix will have 1 minus D over N if an edge is present in the graph, and minus D over N otherwise. So my claim is that the special norm of Mg is going to upper bound the independent set up to some ratio N over D. To see this, we are going to consider S to be an independent set in the graph G. And we consider the indicator vector for the set S, which is 1 over root S for normalization issue for I in S. And then we can just evaluate the quadratic form, like this is the summing over all pairs Ij in S. Each pair gives us minus D over N and 1 over S from normalization. So bringing up together, we get minus S times D over N. And by special theorem, we also know this is going to be lower bounded by the smallest eigenvalue of Mg, which by random matrix theory, we know this is roughly minus 2 root D. So unpack everything, we get a lower bound, or we get upper bound of N over root D. Make sense? Cool. And a lingering question at the moment is special algorithm optimal? There's a huge gap, N over root D versus N log D over D, and can we beat this gap? To answer that question, I'm going to introduce sum of squares hierarchy first. And this is a generalization of special algorithm you can think of. This is a hierarchy of convex realizations parameterized by a degree D, which is usually called a sum of square degree. I'm going to use capital D to distinguish from the small d for the average degree in the random graph sample. And all we know is degree 2 SOS captures the basic SDP or the special algorithm that we just saw. And degree D SOS can be solved by an SDP of size n to the O of D. So when D is constant, this is corresponding to polynomial time calculation. And we know that for maximization problems, the higher degree we go, like it gets closer and closer to the ground truth. And the question is, how large the degree D we need to go to solve the refutation question, in which I mean, when does SOS stop fantasizing that there is a huge independent set in the random graph sample we are given? And yeah, maybe I need to give you some brainstorming about why this might be the optimal algorithm we have. So for many combinatorial optimization problems, it captures the best known algorithm. For example, it captures MathCalc, like the Gaussian SDP is just degree 2 SOS. And Sparse Calc, ARV is captured by degree 4. And we also have exponential time algorithm for UG. And for many average case problems, we no longer have NP harness. They only apply to worst case problem. So we think of SOS as a proxy for algorithmic harness. I hope you buy this argument. And previously, on the sum of squares lower bounds, we have strong sum of squares lower bound for CSP, for a large class of CSP that suppose pairwise independence or some generalization of that. And this culminates in the final work of Katari, Mori, O'Donnell, and Wimmo into this system. And also there is this closely related question to what we consider today, plainly click, in which you sample a graph from Gn 1/2, and you ask whether there is a click of size root n in the random graph sample. There are a lot of efforts, and finally there is this amazing work by Ballard, Hopkins, Kellner, Qatari, Mercer, and Pedestrian that resolved this issue. It resolved this question, and then there is some recent progress by Peng and Qatari Manaha that considers some downstream problems from plainly click. Also, for other dense graph problems, we also have the Shenton-Kirkpatrick hamiltonian. If you're not familiar about that, just consider it as mass cut on random graph, mass cut on Gaussian input graph. And this is also resolved in the work by Gauss, Jones, Pedestrian, Lagrangian. But we know a lot about dense graph because Gaussian input we can think of as dense graph. Plainly click is clearly a dense graph problem. We don't know much about sparse random graph, even just for degree 4 SOS. And in this work, we basically say for sparse random graph, spectral algorithm is essentially tight. If you have average degree at least log square, we can rule out little of log n time SOS, degree SOS. So this corresponding to polynomial time SOS. And we got stronger result if your graph is slightly denser, like if you have n to the epsilon average degree, you can get n to the delta degree sum of square slope. This is our mention, the technical state. And for the experts, I want to emphasize that our SOS lower bound exhibits a polynomial DSOS decay in the objective value. So this is an improvement from plainly click, which the objective value is going to decay exponentially with respect to the sum of squares degree. Okay, and here will be the outline of the talk. Yes, because you basically you pull a vertex out, you see half the vertices. Yeah, you can rule that out. Yeah, but this the poly DSOS is actually not inherent here, and we are going to adjust that later. So to see the power of SOS, we first want to
How does this show that spectral is essentially tight?
Because we see we are saying that for higher degree SOS, the result, like the upper bound it gives is still roughly n over root d. It doesn't improve much from the spectrum. Okay. So we want to formulate a problem, a combinatorial optimization problem using polynomials, in which we can consider x as an indicator vector for independent set and of size omega. Think of omega as n over root d for the talk. The question of whether there is an independent set of size omega, we can ask it as the following. Is there a solution for the following set of polynomials in which xi, xj is 0 if ij is connected in graph because you have the independent set. And sum of si equals omega, the size is large. And xi is 0, 1 variable, so it's Boolean, xi squared equals xi. And if we have unbounded computational power, like we can somehow access the distribution of omega size independent set, then we can take expectation over this, because this is true pointwise, so it's also true with respect to the expectation. And moreover, this expectation is also closed for any polynomial q, like we can multiply any polynomial q. And because this is a Fourier distribution, we have 1 equals 1, everything is normalized, and the square polynomial is non-negative. And to see the square polynomial being non-negative, we are going to think of it as we have a moment matrix, and the moment matrix is going to be PSD. However, we don't seem to have unbounded computational power. So we are going to relax this a little bit and say we only ask for these conditions for degree d polynomial. So we are going to say, okay, q is of degree at most d, and then we are going to add a tilde to our expectation operator to remind ourselves that we are not working with true expectation or true distribution. And we are going to call this the pseudo-moment matrix. And of course, we are going to also restrict some monomials of x to be some subset of size at most d. And here is a good old recipe for proving sum of squares law. It usually comes down in constructing a moment matrix M such that it satisfies problem-specific constraints. And for our case, it's going to be independent set and the size being large. And then we want to show M is PSD in the end. So prior to 2016, the construction requires a huge amount of creativity, and That's where the fun was usually at. And after plenty click, we found a mechanical construction that usually almost immediately satisfies all the problem-specific constraints. However, we still need to prove the matrix is PSD, and the analysis is usually quite involved. But let me start by telling you how we construct the mole matrix. And this is the idea of pseudo calibration coming from the amazing work by Barack Hopkins et al. The goal is to construct the mole matrix E tilde, which will be the mole matrix that we want to work with. And we can think of this as a function of a given random graph. And think of the random graph as given to us in plus minus function. And the idea is to use Fourier analysis for any subset S. Think of it, we are trying to assign the moment for E tilde XS. We can think of this as a function of the random graph sample. So if there is a basis for the random graph, we can use Fourier decomposition and write it as a function of the graph. And it turns out that the collection of edge set is an orthonormal basis for the random graph. So for example, here we have edge between 1, 2, 2, 3, 4, 5. This is one of the basis elements for a random graph sample. But that being said, there's some technical issue that we are going to work with p-bias basis here, just to have mean 0 and variance 1. But if the edge is present in the graph, you are going to get roughly minus root n over d. And if not, you are going to get root d over n. So it's a super spiky random variable. But this is just mainly for normalization issue. So let's get back to pseudo calibration. We know that, okay, for any set S, when we are trying to assign the moments, we want to write it as a function of the graph. The question comes down to, okay, how do we decide upon the Fourier coefficient? Because once we get the Fourier coefficient, G of alpha is basically given to us. We are just going to compute it. Okay. And the idea is to use pseudo calibration to determine the Fourier coefficients. Towards that, we want to find a distribution dependent that actually has a large independent set. And for any graph G coming from this distribution, because we know they have a truly large independent set, you can set the mole matrix to be the moment of the X, the true indicator vector. Yes.
Question, Jack, can you go over the Fourier decomposition again? I missed what you meant by orthogonal basis of the graph.
The orthogonal basis, the graph, for any function of the graph, you can write it in this basis element. And then this is orthogonal. I'm just observing that when Gij is minus this kind of p bias character, when you take expectation of over G coming from G and D over N, each character is mean 0 and variance 1. Okay. Yes.
So, okay, the graphs is just every element with all possible sets of edges.
Yes.
And then your basis is also all possible sets of edges?
Yes.
So your basis is just all possible graphs?
Yes.
And then you bias it?
Yeah.
Okay, got it.
All possible subsets. Yes. You can think of it as a graph. Yes. Yes. Thanks. And yeah, when we have a graph G that truly has a huge independent set, we can just, it's easy to come up with E tilde G because we can set it to be the true moment distribution, the true moments of the X, which is an indicator for the true independent set. And this is a honest score distribution. And if we take a leap of faith and say SOS cannot distinguish these two distributions, like the plenty distribution has true large independent set and null distribution, which is G and D over N, then we can set the Fourier coefficient to be those coming from the plenty distribution by using Fourier inversion formula. Then why might this be a good idea? There are a lot of connections between sum of squares and low degree polynomials. But something we want to observe is that in the plenty distribution, all the problem-specific constraints are satisfied because X is truly an independent set. And to complete the construction, we usually need to truncate on the Fourier basis. And the truncation is usually going to depend on the sum of squares degree. Why is this necessary? Because we don't want sum of squares to utilize high degree information about the graph. Because imagine if you can use like degree n square polynomial of the graph, you can clearly refute independent set. This is essentially a problem about n square polynomial. N square because you need to know all the edges. Yeah. And without truncation, E tilde is also an operator only supporting on the plenty distribution. which is exponentially small subset of the null distribution that we are truly interested in. So, but truncation is okay because before truncation, for any polynomial f that is both a polynomial of graph and x, we know that the expectation is the same because we set the Fourier coefficient to be the same. And this doesn't change if I take the truncation degree to be high enough, as long as the problem-specific constraints are low degree, like degree less than tau, my truncation degree. So all the constraints are still satisfied. Think of f really as the independent set constraint here for intuition. And let's try pseudo calibration in action. The issue is we really need to come up with a distribution plenty that has large independent set, and it's hard to distinguish against SOS. There's some mechanical calculation you can do to determine whether it's hard to distinguish or not, and this comes down to evaluating this change of measure, or which is a likelihood ratio. I'm not going to get into that, but heuristically, as long as this quantity is little of 1, we can attempt sum of squares always. And this is also closely related to the area of quiet painting. And for technical reason, we are usually would like the plenty distribution to be something easy to work with because we are going to manually compute this. So we are done, right? It seems we have all the problem-specific constraints are satisfied, and the moment matrix is PSD in the plenty distribution because we have a true distribution there. So we're good. Not really, because truncation is going to destroy PSD needs, and this is usually the most dirty part. But it usually seems to work, at least for the dense graph when we are working with pentacritic or SK. And it's so technical that people even have a conjecture for this, which is called the pseudo calibration conjecture, meaning the quantity we look at, if it's well behaved, then we get sum of squares over. You can go home. Yeah. So it looks like we have a very clean thing now. We just try pseudo calibration and prove the matrix PSD. But for starters, what's a good plenty distribution in our case? Any guess? We can, of course, sample a graph from G and D over N. And we wanted to have large independent set of independent set of size omega. So we can just sample a set S by including each vertex into the set with probability omega over N, ID. And then we make an independent set. So these would be a good plenty distribution, right? And let's compute the Fourier coefficient. Like for any set T, which is the set of variables we want to assign moments for, we are going to evaluate expectation of xt times g alpha, where alpha is a set of edges, just using Fourier inversion formula. And I can take the expectation over x first and then take a condition on x being an independent set. We notice that each vertex in T need to be in the chosen independent set to get non-zero contribution. And each edge is going to be 0 unless both endpoints are in the independent set. And if both endpoints are in the independent set, it must be a non-edge because it is an independent set. So we get root d over n there. But after all, we are going to say this is essentially the probability all vertices are chosen into the independent set and the number of edges coming from normalization. Then this is just omega over n to v alpha root d over n to the e alpha. This is really standard calculation. And for example, this is a set of edges. T1, 2, 3 is the set of vertices we want to assign moments for. So in this case, we have like 7 vertices and 3 edges. So we are going to set this to be our Fourier coefficient.
Every vertex here is in the S, right?
Yes, we need to make it as, otherwise it's 0. Yes. But there's an issue here. The plenty distribution is not quiet. It's not going to satisfy the condition. It's hard to distinguish against sum of squares. Why? Because you can just look at edge count. Each vertex is chosen into independent set where probability omega over n. Omega is n over root d. So this is roughly probability 1 over root d. So we're going to remove 1 over d fraction of the edges. And this is roughly n edges. However, a random graph sample from G and D over n is going to have edge count concentrated around nd over 2 plus minus root nd. And yeah, n here is much larger than root nd. So this is not a quiet painting. And you might ask, okay, the distribution you come up with is just way too naive. You can imagine you have a distribution that set the number of edges to be equal in expectation. However, those you are going to fail most likely, and usually just going to be cycle count by triangle counting even. And those usually get at least a constant probability distinguisher. So it's still an interesting question to find group plenty distribution. That being said, we don't have plenty distribution. Oh, sorry, your question?
No, sorry.
Okay. Yeah. So that being said, we don't have group plenty distribution, but we still need to prove some of square root. Let's see how we do that.
White planting is it related to the subclass of low degree algorithms? Like, so they not being able to distinguish is basically the same.
Yes.
And I guess here it's for degree 0, but you just allow up to some degree and say.
Yes, yes. Yeah, everything here can be captured in the low degree framework. The question is, okay, we are going to work with the distribution we have, even though we know it's going to fail. That's basically the message of this work. You can forbid sum of squares from exploiting this, similar to how we forbid it from exploiting high degree information from the graph. The distinguisher we know seems to be using these global statistics. You are counting edges or you are counting subgraph. So let's forbid those. And it turns out that to forbid those is really simple. We can just say each vertex in the set of edges need to be connected to a vertex in T, which is the monomial we are going to assign moments to. Otherwise, we zero out the Fourier coefficients. Let's see this in the example. For this one, we have edge 6, 7, but it's not connected to the set of 1, 2, 3 vertices that we are going to assign moments for. So this is not connected. So we're just going to zero out the Fourier coefficient manually. Something nice is e to the 1 is always 1 now, because the only straight connected to an empty set is the empty set, and that has coefficient 1. Very good. Okay. So let's take a look into the PST analysis. So instead, I want to introduce you a matrix decomposition using graphical matrix or using shape. This is a natural basis for SOS mode matrix. And let's consider T to the set of matrix, the set of variables in X that we are going to assign moments to be A, B, C, D. And let's start with the set of edges A, B, B, H, H, C, C, D. We can draw it this way. This is one of the basis elements that contribute to the function e to the xt. Right? But there are also many more basis elements of looking like this, because I can change the label of the middle vertex from H to some other vertex in N. So, and we can see here they look alike. So let's group them together. And grouping them together is equivalent to erasing the label of the middle vertex. So we are going to use this to represent the polynomial summing over GAB, GBI, GIC, GCD. And of course, we are going to require like this vertex to receive a distinct label from all other endpoints. But now I want to say this is a polynomial. And why is this good? Let's see where this polynomial appears. It appears in each entry in the mole matrix corresponding to e to the xt. And where does e to the xt appear in the mole matrix? It appears in many places. So we are going to use 2 additional oval circles, we call it U and V, to indicate which matrix indices we are looking at. And that corresponding to row and columns of the matrix. For example, they appear in the 2-2 split of the mole matrix, like AC is a row and BD is a column. And you can also consider them as being some weirdo shape, like you have MA and BCD in the column. So the circle, the oval circle is not oval here, but it's going to tell you which indices of the mole matrix you are looking at. So again, for now, let's look at this nicer one. You can group over vertices in the circle because right now they have labels. Let's forget the label here as well. This corresponding to summing over different entries of the matrix. And once you sum over them, this is a matrix. Do you agree? Do you buy this? This is really the major proof ingredient towards any SS row on this density. And each matrix has entry that is a polynomial of the underlying random graph sample. because for this one, it's going to be summing over all, like summing over the labels for the middle vertices as long as it's distinct from the other four. And then you have the set of Fourier coefficient there. I hope it's good. So using shape, you can write our Moore matrix nicely in this basis, where n alpha is just the graphical matrix we just defined, and lambda alpha is going to be the Fourier coefficient we obtain from pseudo calibration. And recall that it only depends on the number of vertices and edges. In fact, it has a very nice formula, which is omega over n to the v alpha, and loop d over n to the number of edges. So basically, we are saying the Moore matrix we have is just summing over a bunch of shapes in this formula. So now we just need to show this thing is PSD. It's not that bad because we can observe that if alpha is an empty set and u and v, the two oval circles, coincide with each other, these correspond to the identity matrix, or maybe a scale identity matrix, which is PSD. So if you can show any shape that is not in the diagonal, that is not this diagonal matrix I pull out, is small in special norm, then we can use triangle inequality to say, yeah, this matrix is PSD. This would be the idea. It looks like, okay, this is all we need to show. Unfortunately, the norm is not small for non-trivial shape. So this idea doesn't quite work, but it does give us some insight because it turns out PSD matrix is closed under conjugation. What do I mean by that is that if Q is PSD, then L transpose QL is also PSD. And let's take a leap of faith and decompose the shape using minimum vertex separators for U and V. By vertex separator, I mean, okay, maybe it's really a set of vertices that block all the paths from the left to the right. Okay, maybe let me give you an example for those things. Oh, I think it's fine. I don't think we have markers. Yeah, it's fine. So for, oh yeah, I think I have an example here. For example, this case, for example, for this graph, we want to block all the paths from the left to the right. So a vertex separator, you can fit these two, you can fit these two. In fact, that was the smallest one. You can just fit this vertex. Of course, you can also fit this one. Each of them is going to be a minimum vertex separator. So this is one of them. And we know, yeah, we can see that this other vertex is also minimum vertex separator. But we are going to decompose using the leftmost one and the rightmost one. Let's assume they are well defined. So what's nice about this is it allows us to decompose the shape of this thing to be three shapes. We can call it the left, middle, and right part. And this essentially corresponds to matrix multiplication. Right? The matrix corresponding to the top shape is going to be the product of the three left, middle, and right. Yes.
Why are those things multiplied?
Oh, the left
Why
and
is there a left post and a right post?
yeah, basically you can send flow around, and then if there's a left, okay, I guess it's a bit technical. Let's take it off. Yeah. And after we decompose them into left, middle, and right, you can group over the left and right middle shape. And for left shape, we call it left shape as long as the right part is the minimum vertex separator. And a shape is a middle shape if the left and right part are both the minimum vertex separator for the given shape. And we group them into the matrix Q. So this will be our LQL transpose decomposition. And what's this decomposition buying us? Why do we need to go through all this? It's because the inequality that we want to show earlier, which is not true. It's not true if you have this decomposition. But if you constrain yourself to be alpha, there is a middle shape where the left and right part are the minimum vertex separator. You can control this quantity now, which means you can use triangle inequality to show the middle matrix is PSD. And if you can furthermore show EQ that is essentially L transpose QL as we desire, then we are done because it's a PSD matrix. But before that, let's maybe get some intuition why restricting ourselves to middle shape really helps. And to see this, we want to do some matrix non-bounds. Because we want to bound this quantity, which is a sum of Fourier coefficient times a special norm of m alpha or m tau. We want to bound it by some quantity. And the key quantity to
One question. So this conjugation thing, is it really like you're working in a different basis than the Fourier basis?
yes, you are basically restricting to, you are projecting yourself to some eigenspace of that is a function of a random graph.
So is it something like in hindsight natural, or is it just something which comes up in the analysis of basis?
I think it kind of comes out in the analysis. Yeah.
Oh, really different from how stuff was on PSP, though.
Yeah.
We were also trying to find a different basis where it becomes obvious.
Yes.
That's the kind of like
But yeah, I think CSP is very different because you have some local phenomena. And these like PSC analysis for planar clique or these kind of problems are really global. Like we don't have a local distribution. I think that as the closure for CSP is quite important, which we no longer have. Yes.
Can I think of, because your the pseudo expectation is defined as a kernel, so you have to do this kind of thing because you want to show that the middle part is TD, not just PSP.
It's,
But without doing this decomposition.
even though it doesn't have kernel, you still need to still need this
Wait, so it
decomposition.
doesn't have a kernel, or does it?
Not in the kernel right now. It has a kernel.
Okay.
Q has a kernel.
So then this decomposition is necessary.
Yeah, but it's still necessary even if you don't have the kernel.
Okay.
Yeah. But I guess the key quantity we want to understand is how does the special norm of graphical matrix behave now? And ideally, we want to relate it to some combinatorial property of the shape. And I think, okay, many people told me not to do trace method in a talk. So maybe let's not do that. But the idea is just, it's very simple. You're saying that the trace is regarded as a sum of squares of eigenvalues, and which upper bounds the special norm. And each term contributing to the trace is a crosswalk in the complete graph. So maybe let's take a look at an example. And the counting is usually done by an encoding argument. That's rather standard. So let's take our favorite Z shape. If we do trace method on this graph, you are going to count walks in the complete graph that looks like the following weird shape. And this, we are going to take it to be a length 2Q walk, so some higher power for the counting. And let me try to give you some intuition for non-bounds of graphical matrix when the underlying graph is coming from a dense graph. The non-bound is actually going to be decided by the minimum vertex separator, which we are evaluating this quantity. We take the maximum over all separator and V alpha minus Vs. So it turns out that minimum vertex separator, you want to minimize the vertices in S. So this is how MVS comes up in SOS row bound. And the intuition is really, we should think of each vertex in the separator to be fixed throughout the walk. So it doesn't contribute anything to the trace. And each vertex outside appears twice. The first time it appears, it gives a factor of n, and then the second time we saw it before, so we can use it because we are taking a length Q walk. We can use a label in Q, and Q is a log. So, and by the way, I'm hiding Polar log factors. And the example is this graph, which is our usual adjacency matrix with identity removed, and we know that this is a Wigner matrix which has special norm root n, matching the bound we have up to Polar orders. And for the Z-shaped graph, we know that, okay, you can take these two vertices to be the minimum vertex separator, and you have three vertices outside. So it's root n cube for the non-bound. But since they're different for Sparse and graph, let's see what differs. The quantity that is controlling the non-bound is slightly different. It's still you are taking a maximization over separator, but now edges inside the separator are going to matter. What's the intuition? Each vertex outside is inside. We should still think of it as being fixed, and outside is still going to appear twice. Everything here is the same. However, P bias random variable no longer has bounded higher order moments. Like they're going to grow by root n over d. That's why edges inside is going to contribute to the norm. And yeah, that's how we show the non-bound. And now I want to tell you a little bit about the heart of our PSD analysis, in which we want to show the middle matrix Q is PSD. Let's recall that tau is a middle shape. If U tau, V tau are both minimum vertex separator, for example, the Z-shaped graph is a middle shape. Like you can take these two vertices to be the minimum vertex separator, and the other two is also a minimum vertex separator. And it appears in our zero-mode matrix with coefficient omega over n to the v tau root d over n to the number of edges. And the non-bound, as we said, is going to be this quantity. Root n to the vertices outside and root n over d for each edge inside. Let's see how we can show lambda tau m tau to be bounded by the diagonal corresponding to u tau, which appears with coefficient omega over n u tau. I'm going to, a reminder, omega is n over root d, roughly. Let's just normalize things a little bit so that we just need to say this thing is less than 1. Any idea? So because we know S is a separator and U tau is a minimum vertex separator, we know the side of S must be bigger than U tau. And we know, okay, let's pretend every vertex in tau is connected to S. This is because each vertex in tau is going to be connected to U tau, the left or the right part, by our truncation. I think this is something you can stay at for a second and believe it. And once you are connected to the left or right part, I'm going to claim that any vertex in the left is going to have a path to the right. Otherwise, we can remove that vertex from the separator. And it's going to give, it's still a separator because it doesn't have any path. And however, this violates the condition that the left and right part are the minimum vertex separator. So this path must be blocked by the separator S. And this is a path to S. And why would these two ideas be useful? Now we can assign, okay, let's look at this quantity. These two are helping us because they are less than 1. So the only issue we want to handle is that we can charge the root n in the non-bound and then root n over d in the non-bound as well. We know each vertex outside S is going to come with a vertex decay of roughly 1 over root d because of size constraint from the MVS. We have enough vertices outside for the vertices outside. And each edge, so we can consider a BFS process from S. And this is possible because everything is connected. And for each edge leading to a vertex outside the separator, it comes with a coefficient root d over n. And we know that for each vertex outside the separator, you contribute to the non-bound root n. So putting all these three together, you get a quantity less than 1 for each vertex outside the separator. And finally, to handle the root n over d for edges inside the separator, we just notice that they also come with root d over n in the coefficient. So this quantity is clearly less than 1. So we also need some extra careful counting to afford a triangle inequality over all possible shapes. And the insight we need for the counting is that each subgraph of a sparse random graph cannot be too dense. So this really helps us for the counting. And we should only pay attention to shapes that are not too dense. Maybe something slightly complicated here is that the subgraph we look at is actually not small. It's actually going to be n to the delta size, which is much larger than the girth of a linear graph, than a sparse random graph. So that kind of introduces some technical complications. But for the experts, you can think of this as a matrix analog of the low degree polynomial, the low degree likelihood ratio. There you are just you are computing the variance of a scalar, and then special norm is an analog of variance for matrices now. So this allows us to wrap up the PSD analysis because we have already shown Q is PSD. Yes.
Wait, what does it mean? Is a matrix value likelihood ratio or something? Or what do you mean by
the analog?
Yeah.
Yeah, because I think in scalar you're just computing variance.
Right.
And think of special norm of a shape as a variance. Yeah. And Yeah, because we show the norm is small, we can already apply triangle inequality to show Q is PSD. Almost, because as Tim pointed out, you have a kernel there, so we need some more extra care there. But there's another technical issue, which is E tilde is not quite L transpose QL. And in fact, it's very far away from being true, as we are doing matrix multiplication and since can go a little bit wild there. For example, like we ideally want to decompose the shape we have using this tree multiplication. However, vertices might collide with each other, and that introduces an annoying issue. I'm not going to get into that. Hopefully, yeah. This is the most technical part of the work, usually. And let me wrap up my talk here. It looks like our result is essentially tight if your graph is somewhat dense, the average degree into delta. And for D, that is a Fourier law degree. Brute force algorithm is going to take n over 2 to the n over Fourier log because you are going to just enumerate over all subset of size n over Fourier log. However, our current lower bound only rules out degree log n sum of squares. So there's a huge gap right now. And I think an immediate question is, can we close this gap with current techniques? And this comes down to improving the decay here. We expect the decay to be 1 minus p to the sum of square degree. So yeah, this is the logarithmic trade-off there. And it's also interesting to ask for sum of squares lower bounds for other sparse problems like density K subgraph, like log density. And maybe more ambitiously, you can ask for mass cut. Yeah, thank you. And I hope this picture makes sense for you now. That's really a matrix. Yeah, thanks. Any questions? Yes.
I hope the lower bound for chromatic number.
Yeah. So I think chromatic number, even for the dense graph, you don't. Yeah. But I think with Peter and Pravesh's technique, we can show a similar lower bound for chromatic number for sparse channel graph by using our result kind of black boxy. Yeah. But yeah, I think it's a very interesting question to get a true chromatic lower bound for dense graph even. Yes.
So with the analogy with like these quiet planted objects, is there an analogy for what the distribution we're constructing as hard for SL problems?
Yeah, so what do you mean by analogy?
Like, okay, you started by describing this, take a random graph and then delete the edges within some subset. Like, you did all this additional work to do these new weightings and everything. Does that change what the like analogy planted distribution is? Or is it sort of more like a different truncation?
Yeah, I think it's more like a truncation because it's not clear to us why there's even a distribution of graphs that is like with the same Fourier coefficient like that.
So we have no idea how to pass it.
No, we don't. Yeah, I think it's a very interesting question. Is there a distribution that matches the moments like that? But I don't think there is likely. But I'm also not sure. Yeah, thanks. Question?
I have a technical question.
Yes.
So after truncation, do you need to fix the pseudo expectation to like satisfy the constraint?
No, because we truncate with respect to the independent set constraint. You can think like as long as you take the degree large enough, like you can think of independent set constraint as only some polynomial on vertices in U and V, and the truncation is going to preserve that. We can factor that out and then truncate.
Oh, so after truncation, every constraint
it's still satisfied up to truncation error. But yeah, up to truncation error coming from factorization.
Okay, and you just show that that's
yeah, that's rather low order issue. Yeah.